Approaching to the fourth session in the afternoon, we are grateful to have Mr. Henry Wong with us. Henry is a data scientist and contributes to academic research in the field of black hole physics. He would like to introduce PyTorch Lightning, a deep learning framework that streamlines the process of building, training, and scaling models, allowing researchers and practitioners to focus on innovation. Let's give a round of applause to Henry. Time to skip tedious steps, spare efforts with PyTorch Lightning.
So thanks for the introduction. Hi everyone, thanks for being here today. I'm really excited and honored to have my proposal accepted for PyCon Hong Kong this year. Today we will be talking about PyTorch Lightning, which is a deep learning framework that simplifies the process of training and fine-tuning neural networks. Before we start, I would like to share a bit about myself. I'm currently working as a data scientist at OCL with 4 years of experience in Python. I had the opportunity to work in a variety of projects about video analytics, survival analysis, physics-informed machine learning, and time series forecasting, and so on. Other than that, I'm also a master's student and a researcher in astrophysics. Most recently, my focus has shifted towards discrete optimization and Bayesian statistics. And here you may find the important QR codes for today's section. The QR code for slides will always be in the top right corner, so please take your time and no need to hurry. Now, let's quickly go through what we are covering today. First, we will compare the training implementation of native PyTorch versus PyTorch Lightning through an example of linear regression. This will help us to understand exactly how PyTorch Lightning simplifies the workflow and make our lives easier. Then we'll get into more details with an example of training a deep learning model for image classification. As we go through this, we'll make use of the features of PyTorch Lightning and see the flexibility and simplicity it provides. So here we start from a bigger picture. The content for today is centered around deep learning, which, as you can see, is a subset of machine learning. And machine learning itself is a branch of artificial intelligence. In deep learning, we specifically focus on using neural network to solve complex tasks, such as video analytics and natural language processes. For example, one of the most famous deep learning applications these days must be ChatGPT, which many of you are probably familiar with already. And here we see a visualization of neural network. It is designed to mimic how brain works. By feeding data into the network, it can adjust its parameters through a process called backpropagation, so that it learns and gains the ability to handle specific tasks. We will not dive too deeply into neural network today, but it is helpful to have a basic understanding if you are not familiar with deep learning yet. And here we have part of the results from the Python developer survey conducted by JetBrains, showing the most commonly used machine learning frameworks. While we see SciPy and scikit-learn are very commonly used frameworks, they are not specifically designed for deep learning, so they are a bit outside the scope for our talk today. Oh. Sorry. Then we can see PyTorch and TensorFlow are mostly used. For TensorFlow, most developers prefer using its high-level interface Keras, which simplifies working with TensorFlow. Keras and PyTorch are most likely the starting point for most developers in the field. And now we finally see PyTorch Lightning comes in at just 14%, which seems to be quite low. So does it mean we should leave now and just use PyTorch or Keras? Well, not so fast, and we'll see why. So just like many developers in the field, my starting point is also Keras and PyTorch. At first, I was really happy with Keras because it is incredibly easy to use and perfect for quickly creating proof of concepts to get some early results. But after a while, I realized that the simplicity of Keras is actually achieved by sacrificing some flexibility. For instance, Keras provides a convenient fit method to train models with specific datasets. However, it does not allow us to customize any specific behavior at each step or epoch. We have to start from scratch if we want to do so. Then I found PyTorch Lightning, and it is exactly what I was looking for. First, it is easy to learn and migrate from PyTorch since it is built on top of PyTorch. If you are already familiar with PyTorch, you'll find the transition to Lightning is super simple. We can keep the flexibility that PyTorch offers, but without any repetitive boilerplate code. Lightning handles things like training loops, distributed strategies, logging, and much more. Still, it allows us to maintain full control when we need it, so that we keep the simplicity without sacrificing customization. So, talking is easy. So let's show some code to check out what PyTorch Lightning really does for us. We'll go through an example of linear regression, where we create a basic model that predicts y for given x. In the example, we will first implement the training in native PyTorch, and then we will switch to PyTorch Lightning. This simple task will make it clear how Lightning simplifies things. To implement a training in native PyTorch, we typically go through 5 steps. We first define the model, then we set up the dataset. Next, we choose an optimizer and optionally a scheduler. We also need to define a loss function to guide the model's training. And finally, we write the training loop to handle forward passes, backpropagation, and optimization. Now, let's start by defining the model. Here we are creating a simple linear regression model by subclassing NN.module, which is the base class for all PyTorch models. In the initialization method, we define the input and output dimension and set up a single linear layer using NN.linear. This layer will map our input to the output. Then in the forward method, we define how the input data flows through the model. Then we create a simple dataset for linear regression using torch.linspace to generate input data x. And then we generate the target y with some added noise. We package this data using the tensor dataset in PyTorch, which is then passed into a data loader. The data loader helps us to manage our data with key parameters like batch size and whether or not to shuffle the data during training. We also create a separate data loader for validation, but here we use the same dataset for simplicity. Next, we define the optimizer, scheduler, and loss function. Optimizer adjusts the model's parameters during the training to minimize the error or the loss. Here we use AtomW. We also set up a learning rate scheduler, which optimizes how the model learns during the training. Here we use step learning scheduler. And for the loss function, we use mean squared error, and this will guide our model by measuring how far off its predictions are from the actual values. And the optimizer will work to minimize this error. And finally, we set up the training loop, which runs for some number of epochs, covering both training and validation phases. On the screen, we see the code for training phase. First, we move the model to the training device, typically a GPU, and switch it into a training mode. And inside the loop, we feed in batches of data from the data loader. And for each batch, we clear the gradients in optimizer, compute predictions and loss, and backpropagate the errors and update the model parameters. Then we move on to the validation phase. Here we switch the model to iteration mode, which turns off some training specific behaviors like dropout. Then, similar to training phase, we feed in data and compute prediction and loss, except we do not update the model parameters. And as we can see, this training and validation loop involves a lot of boilerplate code, which are things that we need to handle for every training process. And we have to manage tedious details like ensuring the model and data are on the same device, and manage those nested loops for batches and epochs. Debugging this can sometimes be painful. And in the following, we will see how PyTorch Lightning can help us with this. So here we first compare the steps to implement a training in native PyTorch and in PyTorch Lightning. The core steps remain the same, but PyTorch Lightning we organized them into 3 components, which are model, data module, and trainer. And we will see how. First, we start with a model in PyTorch Lightning. The first change is simple. Instead of subclassing NN.module, we now subclass the Lightning module. This unlocks a lot of built-in features in PyTorch Lightning, and we move the optimizer and scheduler setup into a new method called configure optimizers. And unlike native PyTorch, we now also define the interaction between the model and data within the model itself. By returning the loss, PyTorch Lightning handles the repetitive processes like backpropagation and clearing gradients. Next, we define a data module. We basically just need to initialize a class with Lightning data module and put the original data loader into it. And finally, we define a trainer. Here we don't even need to write a class ourselves. We just need to initialize the trainer class with key parameters like precision and max epochs and accelerator. PyTorch Lightning will handle all of the repetitive processes like backpropagation and so on. And here you may say, PyTorch Lightning is just a wrapper of PyTorch. There's nothing special about it. But PyTorch Lightning is definitely more than just a wrapper. It combines the flexibility of PyTorch with the simplicity of Keras. In the following, we will dig deeper into the functionality of PyTorch Lightning. Again, we will go through an example. This time we will train a deep neural network to classify images in CFAR10 dataset, which is a popular dataset in machine learning research. With this example, we will demonstrate more basic and advanced features of PyTorch Lightning in a more real-world scenario. First, let us introduce more about logging in PyTorch Lightning. Lightning supports integration with multiple model iteration platforms to track your training process, metrics, and hyperparameters. Some popular options include Comet, Neptune, and MLflow. Today we will focus on TensorBlock, a powerful tool to visualize the model performance. We choose TensorBlock because it is easy to set up, supports both remote and local logging, and is the default logger of PyTorch Lightning. Now let's look at how training metrics are logged in PyTorch Lightning. When the trainer starts, if no logger is specified, then a TensorBlock logger is automatically initialized by default. And inside the training step, logging is simple. We just need to make a self.log call to track the metrics like training loss and accuracy. This makes it easy to monitor the performance of our model during training without any extra setup. Other than metrics, we can also visualize some data that we are training on. In this example, we use torch vision to plot a grid of of sample images from our batch. Then we log the generated image to TensorBot in just one line of logger call. And this will give us a visual preview of the training data. Also, we can log a confusion matrix as a more advanced metric for us to understand how is the model doing. In the validation step, we store additional informations like true labels and the predicted probabilities. Then at the end of each validation epoch, we use this data to plot the confusion matrix, and this will give us a clear visual of how well the model is classifying the data across different categories. Okay, so we will have a video because I don't want to test in production. So here we import all the things, and the first thing we do is to initialize a TensorBot, and then we get the link from the terminal, and then we open a browser and type the link on the browser, and we can see there's nothing in the TensorBot because we still not running any training yet. So we import all the things and initialize the dataset and data module, and then we will run we'll define the hyperparameters and model and trainer, and then we'll run the training. So here you can see the training is running, and then we can go back to TensorBot and refresh it. So now we can see the training results. So here you see some images like the confusion matrix we just mentioned, and then we also see other kind of validation metrics. And here we see some sample images in the training data, and also the validation. And here we have some interactive blocks, which are like the training accuracy and loss, and those things we just use self.log to track. In PyTorch Lightning, logging hyperparameters is also easy. We just need to keep a dictionary and call the built-in method in the Lightning module. And in the following, we will run multiple trainings and search for the best set of hyperparameters. Since we have already logged the hyperparameters, the only thing we need to do is to define a metric to evaluate them. Here we use a validation precision as our hyperparameter metric. And the higher the precision, the better the hyperparameters. And we just use the self.log function with the name HP_metric. And here we will see the results on TensorBot again. So here we define the hyperparameters, and then we define a function to generate some set of hyperparameters, and then we run the training, and then we can see on the TensorBot again, in the hyperparameters page, we can see the hyperparameter setting and the corresponding hyperparameter metric in a parallel field. And here we try to skip the training process in the middle because it takes some minutes. So after those training, we see different set of hyperparameters and the corresponding hyperparameter metric, and we can see simply get the best set of hyperparameters by just putting the cursor on the corresponding metric value, and the set of hyperparameters will show on the below. And after some visualizations, we move on to talk about the callbacks in PyTorch Lightning. This is something we exists in Keras but not in native PyTorch. And they are indeed powerful tools that let us add customization during training. And in the following, we will cover two of them, which are early stopping and model checkpoint. We have the flexibility to add more, but here we try to keep everything simple. To add the callbacks, we just need to initialize them with some key parameters. Here we configure the early stopping callback to monitor the validation loss. If the validation loss stops improving, the training will automatically stop. And we also set up a model checkpoint callback to store the model weights that perform best on in terms of validation loss. Once the callbacks are initialized, we simply pass them to the trainer, and PyTorch Lightning will handle the rest. And now we will see how exactly it works. So after initializing the callbacks, just like we show on the slide, and then we also initialize a hyperparameter. Here we set a very high learning rate so that the early stopping will work because the model cannot learn. And here you can see the validation loss. And after like 2 epochs, the training stopped because the validation loss does not improve anymore. And we also see the model weights. Here we add some content for more advanced customization in PyTorch Lightning. First, we introduce Slack, a communication platform just like Discord or Teams, and it offers a easy-to-use Python API. We'll use Slack to demonstrate how we can create customized callbacks in PyTorch Lightning for more interesting use cases, such as sending notification when the training has finished an epoch. The first thing we need to do is write a Slack client. However, since it is a bit outside our scope today, we won't dive into the code details, but the key idea is to create a client that listens to a Slack channel. And this client will monitor for a specific message like stop and trigger specific action in code. With the Slack client, we can write a Lightning callback class. This callback runs at the end of each validation epoch, and it logs the best precision to Slack and check whether a stop message has been received. If so, it will terminate the training at the end of the current epoch. And now we will see the demonstration. So here we see the we see the model will send the precision to the Slack channel, and we can see here. And after some epochs, we try to write a stop message to the channel, and the callback will react to the message you send to the Slack channel and stop the training. So you can see the training is stopped. And other than Slack, we can also integrate PyTorch Lightning training with a wide range of choices based on the specific requirement of our training. So we can also integrate with like Discord or some data science pipeline like Casual or MLflow. And before we wrap up, of course, there are more useful features in PyTorch Lightning. For example, data hooks, distributed training, and profiling, and so on. However, we do not have time to cover them in today's section. If you are interested, please check them out on the website of PyTorch Lightning. And what I have shared is pretty much all I get for today. To summarize, PyTorch Lightning retains the flexibility of PyTorch, but wrap it in a more user-friendly and scalable framework. It is a great option if you want to reduce boilerplate code and focus on the training models without needing the full control over every details. And thank you for listening.
Thank you, and we would like to open the Q&A session to the floor. Yes.
So personally, now you recommend start from PyTorch because of PyTorch less in the TensorFlow.
Sorry?
I mean, like I want to start, which one I should choose? Personally, you recommend PyTorch.
So quite depends on your use case. If you just want to get a taste of deep learning, I would recommend Keras, which is the high-level interface of TensorFlow. But if you want to dig deeper, so I will first introduce PyTorch, which you can get in touch in all details in the deep learning training. And like how do you clear the gradients in optimizer, and how do you run scheduler and run training and write all the things. And then after you get familiar with those things, you can switch to PyTorch Lightning to get a more optimal solution for your training.
Any other questions? If no, next session will be at 4:40. Thank you.